well, this talk, there's a little bit of maths, but not too much, so you can relax. It's very much, it's a lot of it is a personal journey of mine through formal methods, the Whence part, and also a little bit thinking about the future with the Whither part. So we'll see if the Whither part is correct, but I've got some ideas of what I think might happen. When you come up with titles, I talked to Steve Bourne, who did the Bourne shell on Unix, and he told me if you're ever giving a talk and you don't know what you're going to say, just put : Whence and Whither. That was anything. So that's why that's called it. Another thing I learned from Moshe Vardi is any talk nowadays you have to put and artificial intelligence. Well, Ali told me that after I did the title, but and artificial intelligence, because there will be a little bit of that for the future and so on. So, well, Keith has kindly mentioned some background. This is just a very quick show of places I've been, things I've done. I do art things, I do mathematics things. So formal methods is one part of things that I'm interested in. And I was at Oxford University for quite a while. Now I'm an emeritus professor at London South Bank. And I've had a wonderful time visiting lots of places, which is the wonderful thing about being an academic. You can go perhaps the newest way to this field, and a lot of formal methods in Macau. Steve Reeves very kindly invited me to New Zealand to have a wonderful holiday. Sorry, because New Zealand you can't visit. Well, people don't tend to visit New Zealand on their way to somewhere. So they have lots of money they have to use up at the end of each academic year to invite people to help to. And also I now go to China quite a lot, East China Normal University, but now Southwest University. I'm an adjunct professor. We do a spring school each year, software engineering and methods and so on. I've done a little bit in industry. There's a few listed places, and perhaps the most interesting for methods is Ultra and Praxis. And I'll come back to that in the talk, because it's interesting to see formal methods in real use, which most academics, we don't get to see that. So this is a Peter Landin seminar, and I almost forgot that. So these have been produced today because you have to mention Peter Landin. And at least I have met Peter Landin, and we organised this very nice event at the Science Museum in London in 2001 with Cliff Jones, who I think is online, Cliff, so thank you very much for that. And we have 4 speakers, all very eminent, Robin Milner, sadly, Tony Hoare, Joe Stoy, and Peter Landin. And well, they all gave amazing talks. And this is Peter Landin's talk, Why Are Things So Complicated? A typical Peter Landin title. And of course, he covered all the things he'd done with Lisp and Lambda calculus and so on. But the main thing I remember about the talk, because it got recorded, it's on a VHS tape somewhere. We must get it digitized properly, but it's as if there's a laughter track in the background. The audience are just, he's making so many jokes. You can hardly hear him for the laughter in the background, because he was an amazing speaker, very quick and saying fun things. So it was a wonderful talk. That's how I remember Peter, and being very brilliant, of course, at formal methods, both for real things and theoretically. So I've got far too many slides, so sometimes I'm going to rush through some bits and slow down for other bits. But I think formal methods is still very little used in practice, but we do have the safety security area where I think that will continue. There have been lots of misconceptions about formal methods in the past. I'm going to give a little bit of guidance on technology transfer, because I have worked in industry and in academia, so I sort of understand both sides of the equation, if you like. And I mentioned artificial intelligence. I mean, for me, I think that's where the interesting thing is going to happen with formal methods. I'm actually very optimistic just at the moment that artificial intelligence is going to be our lead-in with formal methods for the future. I'll come back to that at the end. So I've got a few fun things, like this was a fridge magnet I had. People expect software not to be so good, and obviously formal methods, we're hoping it's going to be better than that. and of course the old A380 and so on. As I think the early A380s, they really did the software before they took off because they knew if they didn't, something would go wrong. I think we'll be happy to know that A380s are slightly better than that now. The other comparison I've always liked to make, which is actually from Jared Holtzman, but there is a Flat Earth Society. It has a few thousand members. I'm not a member, but there are believers. And of course, we have the formal methods community, and there's probably a few thousand members of the formal methods community, all of you here, and a few more, 1 or 2,000. But yes, but I think the problem is, you can get a few thousand people to believe in anything, flat Earth, formal methods. Until we get to the sort of hundreds of thousands of people believing in formal methods, then it's never going to really take off. And we haven't got to that yet. Something like object-oriented programming. It's hundreds of thousands of people who believe in object-oriented programming, but not in formal methods. So perhaps there will be in the future, but not. I guess to start off the Whence, we start with Aristotle. So I gave a talk in 1997 in Athens, and that was just when they found Aristotle's Lyceum. So if you like, perhaps one of the first universities ever in the world, which is the site of his Lyceum. And of course, he was thinking about logic and so on, which is still the basis for formal methods. Logic important, but also proof is very important. So mathematics, we tend to have very simple theorems, but very deep proofs. But that compares with software, where you have very complicated, if you like, theorems, but specifications, and then actually the proofs are all nearly all very shallow, very boring for a real mathematician. Well, that's a picture of Fermat. So I think you can see why Fermat never quite got around to proving his. Looking at that statue, he obviously had other things on his mind. So it took an awfully long time to prove Fermat's last theorem, which we have done now. But 358 years to prove a program wouldn't be quite good for software engineering. So it's a completely different problem proving things in maths to proving things about software. This again is one of my favorite quotes. I'm sure a lot of you know. It's something I very much believe in, because I'm a practical engineer by training, but then I've joined the programming research group in Oxford and learned more and more about mathematics and so on. Certainly Christopher Strachey, who founded the PRG in Oxford, believed he did a lot of things with industry, and he believed in combining theory and practice. And that's something I've tried to do over the years. That's why I tend to go back and work in industry every so often and see what it's like in reality. So the first formal methods paper, well, this is my conjecture. This is the first formal methods paper by Turing. It's not very well known. It's not one of his highly cited papers, and it's a very short paper, 3 pages. It was just in a conference in Cambridge, but I think we think of this as the first real formal methods paper. And it was reprinted by Cliff Jones, again online. Thank you, Cliff Jones, for doing that. And it's sort of analysed in the context of modern formal methods. And it's amazing how similar what he was writing, even in those 3 pages. I mean, he was only proving a very simple program correct, but all the approaches he was using, things that people are used to now. So, well, it's high frequency. It's got, you can't read it there, but it talks about assertions. We're all very happy with assertions now. Talks about verification, and that's very, very normal in formal methods. Even dashed after states. So if you're a Z person, we always think of after states as being dashed. And there they were in his paper for thinking about after states. These are just a few quotes from that with assertions, verifying things and so on. But the way it was written, go back and read it. Could have been written quite recently, some of it. So the standard formal methods approach. And this is Cliff James's paper with Whence. And this was his diagram. So again, you can see the dash states, so showing how the program, it's a very simple program, but how it works, and doing a little proof. This is it rewritten in a sort of more modern style of flow diagram, but essentially the same with assertions and so on there. So this is Christopher Strachey, who founded the Programming Research Group, worked with Turing. I think originally he wrote a program to do drafts, because Turing suggests you do that. Then he looked at Turing and it worked all about first time, so that impressed Turing. This is a quote from Christopher Strachey, which I think is, this he was thinking about in a formal methods way. I think this has sort of come to pass over the years, so it's quite a good vision of what might happen in the future. So what influence did Turing have on formal methods? Well, Langarden was at the meeting that Turing presented his paper. There was no real evidence it had any effect on it. And then, so the whole of the 50s, nothing much happened. And then in the 60s, people like Robert Floyd started rediscovering ideas very similar to Turing. So perhaps if Turing had lived longer, because he died in 1954, he might have promoted formal methods, his approach a bit more, but he wasn't there. Instead, AI happened in the 50s, or first thought about in the 50s. So it was all rediscovered, and Tony Hoare developed it further by 1969. So it's interesting to think what would have happened if Turing had lived longer, the accelerated use of formal methods. And these are the references in Cliff's paper. We see the gap. Most of it got rediscovered in the 60s, at least a decade or more afterwards. So yes, I'm moving along through dates. This is all pre me being involved with formal methods, but I think Tony Hoare's paper on that, an axiomatic basis for computer programming with Hoare logic and so on, was a sort of turning point in formal methods in a way. So that's sort of guided the way for people after that. So I see that as a sort of key point in the element of formal methods. I think you all know pre-post logic, they're still relevant today, so it's been very long lasting. I mean, interestingly, Tony Hoare, I'm going to admit someone, Keith, if you want to admit people, when interestingly, Tony Hoare, assertion's great for doing proofs, and then Tony Hoare retired and went to Microsoft and looked around Microsoft to see what's going on and found, oh yes, everybody is using assertions. Quite a lot of the code in Microsoft had assertions in it, but not for proofs, as he thought, but actually for testing and debugging. So you never quite know, you come up with an idea of how it's going to be used. So thirdly, assertions have been used in a different way than Tony expected. So even the term formal methods, I mean, I had a look on in the dictionary. So, there's all sorts of meanings for formal. We probably mean it in that D one, meaning, logical. And then method, again, some different things you might mean by method, but in the dictionary here, it does actually mention logic from the 16th century. So that's the meaning we mean when we say formal methods. I did have a look at books, names. I've got Google and so on. You could do a sort of search around. There was a 1962 book called Formal Methods. Anyone read it here? It's about logic. It's by a logician and philosopher. So I think it's the earliest title I found with the name Formal Methods in it. Where the name Formal Methods came from is a bit obscure. One time, like software engineering, which came out of NACO meetings and so on, all methods seems to have just appeared. So by the end of the 70s or so, the term was used reasonably widely. We had structured design for that, but then we started to have more of a mathematical basis, and that became formal methods. And of course, there's different levels of formal methods. I mean, you can just specify things, and that has quite a lot of benefits. I mean, I'll come back to that in industrial experience. But actually trying to do proofs in industry is quite a heavyweight thing. But I'm an engineer by training, and engineers don't do proofs. You might do some calculations. Some mathematicians produce something, doing a proof is less common. But formal specification is still very useful. You don't do any formal proofs. So various different approaches to formal methods. I guess, like all communities, things get spread a bit. So there's been the abstract interpretation community, model-based testing, model checking, and when you start doing research and so on, you tend to get siloed into one of these communities. I've been siloed into the mod community because when I started doing research, that was the area I was in. So there are an awful lot of approaches. Some of it has tool support, so proof assistance. Some of it lets you do refinement, helping you get from the specification down to the code. You can just do static analysis, looking at validating things. You can do proper full verification, doing full proof. So they're all approaches. Some of them very difficult to do in a large system. Verification of a large system is very difficult. You might just stick to a specification for that. So these are really, I think, the three levels, if you like. The formal specification on its own is still useful for large systems. You can produce programs in a more formal way as verification, or you can use full theorem proving with a tool to help you do that. So top one easier to do, scales up much better. Bottom one can be hard and expensive, but perhaps that'll change in the future. We'll come back to that in the future. One of the problems over the years in industry is even the IEEE glossary calls it formal specification, one written in accordance to established standards. Well, that's not what we mean. We mean something that's written in a formal notation. But there has been quite a lot of problems with academia and industry talking to each other and using the same term but meaning different things. So that can always be communicating. So in the 1990, Anthony Hall wrote this Seven Myths of Formal Methods, which was, I'm sure a lot of you know, was I think quite useful for explaining to industry what is actually true. We're in the world of fake news at the moment. So he was trying to separate out facts and myths that people believed about, explaining that some of the myths weren't actually true. So in the early 90s, this is when I was moved to Oxford, doing lots of Z things, but then nice European projects came along. Been more difficult more recently, but in those days, there was lots of encouragement to collaborate across Europe. And this was trying to look at, starting with requirements at the top, going through specification, design, programming, and even going down. Once you get to a program, you can automatically go through compilation down to hardware. But of course, these connections between these may be formal, or typically they're formal. So this was looking at actually trying to connect all these different levels. So yes, little stop press. Now that I'm retired, I'm mainly writing history of all the methods papers. So we have actually, there's going to be a nice special issue of the FACS journal, which should be out, I don't know when. Cliff Jones and Jim Woodcock have been organising it, but sometime next year there'll be a special issue, including some reminiscences of the Procos project. Because one thing you often don't find out is, some new approach, oh, there it is, but how did it come about? So in particular on the Procos project, duration calculus came out of it. We didn't know that when we started. And it's quite interesting to see different people's viewpoints of how you get together and come up with a new notation. So, I mean, sadly, the three people involved aren't able now to contribute to the paper, but we had a lot of people there who see what was going on. So this is one thing I like to show with levels of abstraction, because we're trying to prove things and you want to connect these different levels. So you can take these figures with a pinch of salt, but I think there's no point in connecting two different levels if, well, it's an order of magnitude difference in the size of what I'm describing. I think I read one paper which was proving the specification and a program, and the program was about 50% longer than the specification, and the whole paper was about proving that thing's slightly bigger than the specification. Well, I think in real engineering, you need to be doing much bigger steps between the two levels that you're organizing. So, the spec, you might have some design documents that are getting pretty big, lines perhaps. Then you might have, a program 15 million lines long nowadays. Fortunately, at that point, we have compilers, so we can compile down to maybe 150 billion machine instructions. So we're getting quite big now. At least that bit's automated. It might be running on a huge, now we can have billion transistors underneath. So you can see the complexity gets quite big, and trying to prove or connect these different levels. At least compilers tend to be all right if you don't do too much optimization. Hardware people tend to be more formal than software people, because if you make a mistake in hardware, very expensive as a business, as people like Intel know. So, of course, if you make a mistake at any level, you have to go back again, change something. So you can see it's a lot easier to change something early on, made a mistake, than it is if you find you've made a mistake when you've got it all in hardware. That's going to be incredibly expensive. Whereas if you make a mistake at the formal spec level, go back to the requirements, not so much effort. So after New York Falls paper, yes, this is a typical situation where, like Kinchy, we thought, well, we'll do another paper. So we did it in commandments. It's good for marketing. Certainly, it's been used in textbooks and software engineering and so on. I won't bother going through all the different commandments. It's basically things you should do when you're using formal methods that maybe people don't think about. Yes, which I think we were going in the usual way. We were going to do a conference paper and then a journal paper, and then the journal wanted it before the conference. So yes, it got accepted very quickly. Users. And we did a book together, again, trying to show some examples of real use, Tektronix and so on, and IBM Fix, which was a use of both. Well, it used Z and B. We tried to get people to write about how they were using formal methods in industry. A few more, and I guess we did another 7 minutes, but I'm not going through it. But then that was accepted. We look more examples of immune systems. Stuff with radiation therapy. I actually visited in Washington. It's a machine that I think took a third of the electricity in the hospital, shooting things at people's body if you get something wrong. That's so good for them. So that was all specified in and even Microsoft do actually do quite a lot of formal methods. I guess nowadays a lot of things don't get called formal methods in industry. Things like assertions at Microsoft, it's not called formal methods, but they are doing formal things with the assertions. And I quite like this book because most books just say, here's a system we produced, but it doesn't say how that system happened. So although this was using a fairly small example, it took an example, different people showed how using their formal methods approach, what questions you would ask when you produce specification. So there's all these different formal methods, all trying to attack the same problem. It's interesting to compare the different questions that different approaches ask. So I was involved with the Z1, where we're obviously asking about preconditions and all that sort of thing. But different approaches end up asking different questions. These just, there have been various books over the time. So there was a time when probably half the universities in the UK were teaching Z, and we have some people who have written books on Z in well, proper textbooks, mere textbooks. No, sorry, we have a running joke that his book is a mere Z book, but
yeah, beginner's introduction.
Yeah, a mere introduction. Sorry, but it's an excellent introduction if anyone wants to start with Z. But I actually like this is the Jonathan Jackie book I used for my courses on Z as I taught. He was the one who did that radiation machine. So, he had real experience of Z, and he wasn't an academic. He wrote it from a practitioner's point of view, which I liked. The only problem with, so this is a book being sold by one of the students, and you may have noticed. So that's the typical situation that they've been made to get the book, but use it. But anyway, I use this as the for the course itself. So these are just one or two little cartoons that I like. It is quite, if you're from industry, which approach do you use? This is the Z people versus, it says PVS there, but it could be any other formal method. It's quite difficult to know, what you should do, because every formal methods community says ours is the best thing you can do with it. These are two very different approaches, very, very verification theorem proving. This is just more specification. So this is better if you are doing a system. This might be a smaller system, but you want to really be sure that it's correct. Formal methods tools, they haven't been very wonderful. They're still not that. They are improving, but to use a prover is quite a lot of effort to learn how to use a prover. It's fine if you're an academic and you've got 6 months, your PhD, spend 6 months learning to use the proof tool and then do something interesting. If you're in industry, a week is the maximum they're going to train you for, even a month to learn to do something. So if your prover can't be learned to do something useful within a week, really forget about it in industry. And we still, I can't think of it. If anyone knows a proof tool you can learn in a week and do something useful, tell me, because you might be able to sell it to industry. I have been involved with technology transfer quite a lot, I've given courses in academia, I've given courses in industry. So the industrial course I gave for Z, I'll come on to later, but the course had to be less than a week, Z. And Z, after a week, at least you can read Z after a week. Most people, that's all they needed to do on this particular project. Back to that. Learning to write Z takes longer. You need a good choice of textbooks. Z for a while did have had about 15 textbooks, I think, but then you compare it with Java, hundreds of textbooks. So as I said, flat Earth Society style, we're down in the 10 textbooks, and you're in the hundreds of textbooks if something that's really taken off. As I said, you might be able to use things like type checkers, very useful. Use those very quickly, but things like provers then take a long time to learn. So web resources are important. I was involved with a virtual library, which covered lots of things, and I did the formal methods section. But that's now really irrelevant. If I'm doing some methods, I put it on Wikipedia now, because at least somebody might read it there. The nice thing about Wikipedia is, if you make a mistake on it, somebody will come and correct it for you. So I quite like that. It's my notebook. If I get it wrong, somebody will have corrected it for me next time I look. So things like mailing lists are still important. In fact, obviously you need meetings to try and get industry and academia together. Standards, like I'm going to get onto the Z standards, but one of the problems with standards is they take an awfully long time. We did produce a Z standard, which I think I'll come on to. But at least from the 1990s onwards, standards started to be mandate formal methods for some safety security applications, at the highest level. But that was obviously good for getting methods to be used. And this is actually still my most cited paper, doing a survey of these. So anyone who's trying to publish, this is just a little thing as I learned from this. So I've submitted this to one journal and it was rejected out of hand. I submitted to a second journal and it wins the best paper award of the year. So after that, I learned it's a lottery. So don't worry if your paper is rejected. It may be brilliant, maybe too brilliant for the journal. Send it somewhere else and then it'll be appreciated. So there are some standards for the Z notation, for instance, but that took most of the 90s to do. I did find some inconsistencies in Z, so that was a useful thing to do. But then, if you spend a whole decade doing it, things move on. We already had the Mike Spivey standard book on Z, which was fine. And this did various extra things, but I'm not completely convinced how useful it was for Z. I guess it's useful with tools and so on. But, we had a de facto standard Z book. For me, it would have been better with hindsight to say, look, this is the Z standard. Let's get it through in a year or whatever it takes to get it through ISO, rather than spending a lot, has anyone here been involved with doing standards? I don't recommend it. It's a lot of committee meetings and so on. I managed to avoid getting involved with the Z one, but I know how much bureaucracy there was in doing it. And then they tried to start adding lots of stuff to it to accept. Although found a few inconsistencies, whether it was worth it or not, I don't know. I'm going to cover a little real example. How are we doing for time? Because that's okay, a quarter of an hour. I'll try and speed up. So I have worked in real industry sometimes, and this is for the air traffic control in the UK. So obviously a lot of people involved. If you have an air crash, it's a complete disaster. I mean, this project cost in the order of 10, 20 million. Just one crash costs far more than that. So you've got to be really careful whatever you produce. It's going to avoid that. So there's various air traffic control centres around. Yes, just so you know, the airspace is all split up. So anything around an airport has its own air traffic control. Everything above 22,000 feet or so, again, that's general air traffic control. And this is what the centre looks like. So it's incredibly secure. Basically, imagine terrorists going in and trying to wreck this place. So this place can be on fire outside. They can still keep going. It's got about 3 different electricity supplies coming in. So anyone cut off. There was one case with Heathrow recently where they lost it. This is the national one. They're a bit more careful with this one. So, and then there's a whole room full of batteries. So if all the electricity is cut off, it still keeps going. So, it's very important that it never stops. I'll tell a little story after the talk that I don't want broadcast. This is being recorded, so I can't. So before this project, actually, we were still using flight strips, amazingly. Anyone recognize that flight strip? We check on how expert you are at air traffic control. Well, I guess the giveaway is Conch. So this is the last flight of Concorde. It was a nice little souvenir I was given. They did print quite a lot of these, but I don't have the only flight strip. But that's what a flight strip like, and it's going to JFK in New York. See JFK there. And this is what air traffic control looks like around Europe. Now, all countries want to do their own thing because, well, it's a very secure thing. You don't want to rely on other people too much. You can see up here, does this work? Anyway, you can see London there with Scotland is separate. Shannon, SHA, that's Ireland. So England and Wales long there. You can see the whole of the rest of Europe is pretty complicated system. And you've got people coming in from other air traffic control systems, and then you've got to get rid of them again. I mean, I think of it as a bit like the internet, where you've got a load of rubbish coming in packets, and you've got to try and get rid of them as fast as possible. It's just in this case, the packets are aircraft. You're trying to get them to wherever they should be, either out of your airspace or down on the ground. And this is what it looks even. I'm sure some of you have this app. It's quite interesting monitoring. I always have a look when there is a problem to see great big bits of space where nobody's flying and so on. So there is a big project to try and do things together called this CESAR project. I think the last time I gave this talk, it said 2004 to 2020. A quick check, like all projects, so they think about 2030 now. So it's one of those ongoing projects. I suspect it will never finish. So there is a bit of talking between different parts of Europe. Now it's being advertised. So NATs do the air traffic control. Basically, the situation was you so much space in the sky, you want to get more aircraft into it. You have a safety case saying you have so many in a given sector. If you want more, you need a new safety case. So the formal methods in this case was to help with the safety case, say we can have more planes closer together, and it's still the same level of safety. So that, and you might think it's all just free air up there when there was like motorways. So you're flying down little tubes if you're a billion aircraft. But every country, the whole of airspace is by default is military airspace, and they generously allow civilians to use it. But if there's suddenly an emergency, bits get cut off from military again. So a lot of the project I was working on was the military do this, if civilian do that. Interestingly, if for instance the king goes flying, everywhere magically around becomes military airspace. So some people get extra protection. This is what the team used to look like. And I guess one of the things that you have an assistant doing the flight strips. Well, of course, if we're computerizing it, you don't need this person. And you have to talk to the unions and say it's much better with formal methods, but somebody's got to do that job. But then they have a go with it. And they say, well, this is wonderful. We like it. And actually, if you have more planes in the sky, you'll probably need more air traffic controllers anyway. So in the end, that wasn't an issue. Well, you've worked in industry, you know there's lots of acronyms. That's what IFACS stands for. It's still called interim, even though it's still going underneath. So it's not actually the air traffic control, but it helps air traffic controllers. So and it gives you lots of extra information which they didn't have previously. So this is one of the displays that I would like. So if you look at that, you've got time. These are pairs of flights. You've got time to interaction. So this one, 10 minutes away. This one's only 4 minutes away. So it tells you, which flights are going to get a bit close. And they're meant to be 5 nautical miles apart. So anything below this, that's bad. So these ones up here, that's okay. They're never going to come too close. So obviously, if you're an air traffic controller, well, this one's not too bad, but this one's looking a bit of a problem. So you better do something about it. And the system will basically suggest this plane might want to just veer off, avoid this situation, then you want to get back up the line. And game over, as if you already, that's not so good. So that's never happened, fortunately. before either 5 minutes here, well, air traffic controllers could, in their brains, do this up to about 5 minutes. But this thing goes up to 15 or I think 18 minutes. So that gives the extra level of safety. So you can have more planes in the sky in a given sector. So that's one very important aspect. There were lots of other displays as well. So it used Z, thousands of pages of Z, in things like the differential equations for doing all the algorithmic things of flying around the airspace. That was all done in maths. They used Mathematica for it. The interface was just done with state tables, which you can very easily give a logical basis, but very simple. But there was a lot of English. With Z, you always have English describing what you're doing. But it worked very well having the Z and the English. Some people could only read the English. Some people read and the English. It's a very few people can only read the English. I could do both. So, you know, that's just a typical Z from this. Getting largish, but they always kept it down to about half a page. Most of them smaller. This is one of the larger schemas. I mentioned training. So they had a 3-day course, trained about 75 people to read Z. I was sent on the course because, like all projects, it was getting a bit delayed. So they brought in about 10 or 12 engineers, including me. The only difference with me was I had to give the course, so because none of the others knew Z, but I did. They couldn't spare anyone else on the project to give the course, so I did. They do have a Z writer course where you need far fewer people writing Z on a project like this, because most of it is reading it and using it for doing testing. I mean, they say three days and they say 3 months to get fluent. That's cool. 3 months, might be 6 months, depends on. But you can see a good software engineer, you know, who's got some understanding of logic and so on, after a week or two, you know, they can read Z specs enough to use them usefully. This was all done in Microsoft Word, amazingly. I know. So, well, they say because in industry people don't use LaTeX, so to use Word, because that's Nance didn't know about. But they had Word add-in. So actually, to do the Z, Anthony Hall wrote a very nice plugin for Word, which is actually basically LaTeX hidden around the back. They didn't know it was LaTeX. But that meant you could use the fuzz type checker to use LaTeX. So that all integrated quite nicely, having a type checker that was already there, LaTeX and so on. But they had to have a graphical, like Microsoft. So these are written by Praxis for the good things and the bad things. You know, they found it, finding using fuzz was very useful because actually it would actually link back to where the error was in the Word document. So even though it found the error in LaTeX, then sent you back to the right place in the document to say this is where the problem is. It also helped, you know, they could do all the cross-referencing of Z names and so on, because if you're on 1,000 pages with Z, we're used to 10 pages in academia. Once you have 1,000, things like indexing get very important. So it was a bit slow, but you know, perfectly usable. I guess another thing that we don't have to worry about in academia is you're doing a real project, you have various stages of the project, so you keep adding things to the spec, and then you have to merge different parts of the spec at different times in the project. So that was an issue, but it was handled. So. This was their state machine. You know, just press a button and you move from state 1 to state 2. I think you can all understand that. Engineers can understand that. So they didn't need any training for that. And it was just these state machines were just written in Word tables. So. And it was all implemented in Ada, so Spark Ada, which does have a formal semantics. The fortunate thing about Praxis then was, you know, they had maybe 75 plus people, all of whom knew Z, who knew Spark Ada, but no training problem. But this project was actually 150 people, so they did have to bring in another 75, huge project. they already had a good basis of people who could write Spark-aided programs. They could just read the Z, write the program. So yes, if you like, there was no proof connection between program. You had very good programmers who could understand the Z. And actually they could find errors in the Z and say, that's silly, maybe brackets in the wrong place, type of error. And then that Z spec actually used doing the testing. Well, there's some code. It's got assertions and things in it. You don't need to read it. So they did train more people in using Spark-Ada. All the people on this project were very good software engineers. Train them in a new programming language, they're pretty quick. There are some proof. Spark has a tool set of things to help you do it, checking and so on. So probably the formal correctness proofs, I don't think they weren't doing much of that in practice. But the Z spec was actually used to do test design. So this was what a typical test design would look like. It would be looking at some Z spec, which would be called that deviation request thing. And then you're doing partitioning in the head of this. So you have good, when you read Z, this bit may happen, that bit may happen. So this is going through all the different possibilities in the Z, saying, are we doing the test? What do we expect to get out of this, etc. So, if you do that naively, it's sort of exponential expansion of, then else, if then else levels. So actually the real challenge was deciding, well, what tests can we do together and what can we do in the right order to make it easy to do all the tests. So, one example where you might have done 1,000 tests, but with a bit of thought by a good engineer, you can get that down to a much more manageable number. So you still need expertise as well as using formal methods. When the Mathematica was quite interesting, because it's a very small team, but they didn't know Mathematica, so they all had to learn Mathematica, which is just a functional programming language, do all the sort of differential equations part, and then they used Oracle style, using Mathematica to calculate something, a program to calculate something, and then you compare the two. Well, this is real numbers. Of course, they're not going to be exactly the same. So then you have to decide how close they need to be. But interestingly, there was as many errors in the Mathematica as there were in the program. Because they were experts at programming, but not so experts at the Mathematica. But then, if you get a mismatch between the spec and the code, there's an error somewhere, so to look at both of them. So they're pretty heavy. I think they still do various formal methods things. The tool support was very important, but they knew that they could do with more tool support than they had. And I guess one very important aspect of a big system is tracing, which I'd never really thought about that working, not in industry, but essentially if you have 1,000 pages of Z, you want to make sure that everything up in the Z links down to something in the code. And if there's no link, you're not testing something. So this tool is very good at going through all those, and the human can't find all those links. So this would say, I can't find a link between these two. The human goes and has a look at it and says, yes, we need an extra test. Another little story I'll tell you afterwards about testing, but some things can't be recorded. So, they've continued. There's still FACS, I think, running underneath the system. So it gives you 18 minutes of prediction. I mean, they've added more software that lets you do prediction of traffic load for up to 4 hours now. So that gives you better planning. It won awards. The military are using it now as well as the civilian. They like it. And there's a successor, which is part of this European project. And I haven't found out too much about exactly what's going on with that. Often when the current things you don't get to know too much about. So going back, mathematics, we all here think mathematics is very important, but some don't think it's very important for doing software. So we're obviously trying to convince people to use more mathematics. Uh, so some others think of it as important. So that's always been a debate, and I think it's still a debate. There's a lot of people writing software that don't take a very mathematical approach to it, which is fine if you're writing games or something, but there's a lot of software systems where you can not only lose lives, but lose a lot of money if you get it wrong. So, I don't know how much Bitcoin's used all methods, for instance. So this is more recently, I've been involved going to China a lot. So there's an amazing amount of stuff going on in China. So we have a spring school, which is a bit like the Marktoberdorf, which I think is down at the bottom. Yes, so obviously we have Marktoberdorf summer school in Europe. And this is like a Chinese version, which we have in the spring because it's quite. So we've been publishing proceedings for that. I mean, interestingly, you notice there you'll see, well, you might not be able to see it, but there's Turing and von Neumann there on the front cover. And they're both at Southwest University in Chongqing. So, I roll up in Chongqing and there's a bust of Alan Turing. So, and it was all paid for by students. So I can't imagine students in this country saying we want a bust of Turing was first, and then a few years later I went back and there's von Neumann. So your question is, who was the third person who they should have a bust for? It's a rhetorical question, I don't know. Only horror. So there's the students at this thing. The latest one we had was in Beijing, so it's probably going to alternate now between the ISCAS, which is the Institute for Software at the Chinese Academy of Sciences, sort of their equivalent to the Royal Society. And well, a lot of the talks have been about formal methods and AI. So we're going to get more now onto the AI future side. Explainable AI. Can we use formal methods to explain what's going on in AI? Still ongoing. So this was another talk by using learn models with AI. This was doing more rigorous correctness and so on. Moshe Vardi, who I mentioned earlier, this talk didn't have AI in it, but he talked a bit about AI and machine learning in his talk. And we combine human intuition with AI. And then more unexplainable AI. I'm just going to rush through these. As you can see, virtually every talk had something on AI in it, even though this is very largely based on formal methods because of the sudden developments in AI. This was on testing. But it's difficult to predict for the future. So, I shouldn't do this to poor Brian Oakley, but this was a prediction in the 80s, formal methods, which sadly probably hasn't come to fruition yet. So perhaps this will come to fruition, but it's dangerous to make predictions. So I'm going to make suggestions, not predictions, of things that might happen. These are just a few future developments. I think you've got to want it used in reality. I'm an engineer. You've got to take a lot more engineering approach, perhaps less proofs, more calculational styles will get engineers more interested. Sometimes a light approach with just specification. Tools, though, proof tools are improving because with Moore's law, we can do things faster, more memory, etc. Standards, well, I'm not convinced how much they're actually helping. Education and training is very important, and unifying approaches, because as you saw earlier, there's a lot of different approaches, and certainly Tony Hoare spent a long time thinking about looking at physics with unifying things. We have all these different approaches to semantics. Can we connect them? And he and Jipeng wrote a book on unifying theories of programming, which Tony has very generously sort of admitted. I mean, it's Tony Hoare and He Feng, who was working at Oxford at the time. I mean, actually, He Feng did most of the mathematics in this, but Tony Hoare is very good at looking at things and suggesting things and simplifying things. So they work very well together, having the two of them, because Feng, I mean, Tony Hoare can come up with an idea. Feng would go away and say that doesn't work mathematically. And they come back and go round, and if it didn't work in the mathematics, then obviously they try another approach. So I think Tony Hoare said that Feng should really be first in this because he did most of the mathematical aspects of it. But it spawned, there's an international symposium that started in 2006. So certainly there's a whole community built up around UTP. And looking at more, certainly I believe that safety critical systems and security and so on, there's always going to be formal methods for those systems increasing. Well, you need to invest in the technology transfer. I'm not sure how much we do in practice. But this is the area I think that is most interesting with the AI coming along. So that's what I'm going to talk about mostly. So these are, I don't do that much research, self-informed method anymore, but I'm in Oxford. I can go to nice talks. I'm about 5 or 10 minutes walk from the Mathematical Institute. And the mathematicians are doing an awful lot with AI practice. So they realize there's something interesting going on, and how can AI help with mathematics? This was just one talk I went to, and how can we discover things in maths using large language models? Well, this was a discussion appeared in Nature. They're just ideas of things we might be able to do in mathematics. So it might be able to suggest outline proofs in AI. So I think personally, I believe there's always going to be an interaction. I don't see AI taking over, just doing everything. But it will take a lot of the drudgery out of the mathematicians and for us, formal methods, doing the easier bits maybe, and then we can do the more interesting bits. So this was for mathematics. I think there's quite a good chance we can do it for proof of programs as well. And this was a nice talk by Terence Teo, who's a field medalist. So he gave a very nice talk in the Science Museum last year, looking at AI for mathematics. So these are just a few of his slides pinched. But of course, proof tools are very reliable. LLM is incredibly unreliable. Fake news versus real news. Can we connect the two? He certainly, well, even then he was looking at the Maths Olympiad, and it was doing quite a lot. This was last year. It's improved more now. So AI can do a lot of the Maths Olympiad things on its own without much help. So he was positing, we've got these good proof tools, we've got the unreliable LLMs, can we put them together? He thinks we can, and I think we can too. So he thinks it's going to be useful for, mathematicians do use proof assistants and so on for doing their proofs. I think we can probably learn a bit about what mathematicians are doing at the moment. I mean, actually, most of the maths we use is about 50-year-old maths, or more. So it's worth having a look at what mathematicians are doing now, things we might be doing in the future in computer science. So he's suggesting you can use AI to fill in maths proofs, and I think we can do that for program proofs.
Yeah.
So those of you at the LMS FACS talk, or say FACS LMS here, we sort of swap them depending on the audience. We had a very good talk by Jeremy Avigad on mathematics in general in the age of AI. So I think the lean tool, which I don't know particularly well, but it seems to be really catching on. It's a proof assistant with a functional programming language. And certainly people are looking at doing AI things with this lean tool. Seems to have sort of come out of nowhere, but if you're interested, there's the URL to go and look at it. But, you know, it seems to be building up a really good community behind it.
Yeah.
And I mentioned the Maths Olympiad from last year. You know, this year it's even better. So it's to, you know, it can solve a lot of the problems in the Maths Olympiad. Next year, you know, probably even better. The development's just so rapid. And he's has some various thoughts on saying, well, that we should ask what technology can you do for mathematicians, but I think we can do that for formal methods as well. Can the AI help us? So this week I've actually spent 3 days in St Catherine's in Oxford, because I live in Oxford, and again, mostly sort of formal methods type things, but AI coming in. This was a LLM approach to doing automated translation of real word code bases, and they're very keen on, we can't read correctness, but you know, they're trying to do it correctly. We're trying to see how much LLMs can help make it easier to do. Still with an eye to correctness. So if you go on to Archive, somebody was asking about Archive earlier, there's a huge number of papers coming out on Archive that are looking at AI and a lot on Lean. So these are just a couple using Lean, doing AI type things. So if you want to keep up to date, Archive is a very good place to see what's going on. And you know, it's happening monthly now. It's not just, because there'll be a new one this month, probably, that I haven't put on. And certainly DeepSeek seems to be doing things with mathematics. This month they've issued DeepSeek Math V2. I haven't used it, but you know, if I was still actively doing things in formal methods, I'd be having a look at this, seeing what it could do for proofs in formal methods. So you can see how rapid it is. But I think all these developments in AI, I'm rather optimistic they're going to help formal methods. So, you know, if I was young, I'd be looking at doing things like trying to make AI help developing formal proofs and so on. Yeah. We might look at the AI winter, which you may have heard of, which things go up and down. Certainly AI has gone up and down through the years. You know, they had 2 major winters in the 70s. And then we had the 5th generation expert systems and things, which suddenly we thought AI is wonderful. And then that all died. So we had another winter, 87, going on to this century. And now, of course, recently, you know, suddenly we're in a boom situation. So I go into Blackwell's, part of my tour. Now, AI right at the top, you know. Well, this is what I'd like to see. Perhaps one day. But I think there's a possibility that AI, you know, we may be not a complete winter at the moment, but it's, you know, not that wonderful for all the methods. But I think with the AI, we can piggyback AI for the future. And I think formal methods is going to become more and more important, getting AI to help do formal methods. You may have heard, who's heard of vibe coding? Right, okay, that's not bad, half the people. So it's the word of the year in the Collins Dictionary. So I think we need to start coming up with our own, you know, we've got vibe coding producing but we need vibe specifying. So please start using vibe specifying in your papers in this. And of course, we need vibe proving, you know. So I think AI is going to help us do vibe proving, you know, it'll give us some of the proof, and then we still have to do some work, but it's going to help a lot. And as an engineer, I think we should be doing vibe calculating. Again, it's going to help, but and you'll still have to use some engineering judgment to do vibe calculating. So I think in that sort of context like this, lots of opportunities with AI. It's just a reflection I've used for quite a lot of papers over the years, but it's a favourite quote about talking about things being difficult. Well, formal methods is difficult, but I think it's going to get easier. I always like to compare why French don't use the word email. It actually means enamel. You have to call it courriel in French. They get confused if you say email. And a bit sad, I think, you know, early pioneers are dying, and Jean-Raymond Abriol, who I'm sure a lot of you know of, and invented basically started three notations and approaches, Z notation, B method, and then the event B approach, all of which are important and still being used in some contexts and so on. So we are planning some tributes in the January newsletter about Turing Mod Gabriel. We had some tributes on Tony Hogg. He reached his 90th birthday recently, so it's going to be something like that. And I'm hoping Brian over there will do some editing with him, who will check the spelling. Because Turing Mod Gabriel was French, of course, so we might need a bit of editing. But there's also an LNCS festschrift planned for Turing Mod, ultimately. I mean, interestingly, he was offered a festschrift, but he's such a modest person. He's like, no, I don't want anything like that. But I'm afraid now he isn't here to say that. But it'd be nice to have a celebration of all this over the years. Definitely deserves that. Yeah. So that's the end of the talk. I'm sorry, I probably overrun. Let me have a look at the timing. Not too bad, only. So thank you very much for listening.
Shall we continue recording for the questions, or shall I?
You can do, because I won't say it. I'll say things over drinks, or the thing that I said I won't say it.
Oh, okay.
But well, if you've got a question where you want me to answer something that can't be recorded, ask me later. Anyway,
Stop record button. Okay, so we have a few questions and comments online.
okay.
I think I will take chair of meeting and chair of FACS privilege and ask you the first question, please. Tools. It was an interesting point you raised about tools, that they're not really quite where they should be for formal methods yet, or?
Well, I think they're improving.
Yeah.
But yes, I think there's no easy proof tool. Maybe Lean looked at it more, but you need a lot of training to use a proof tool. Do you know a proof tool that you can learn in a week? No. So that's what we need if you want it used in industry. If we could come up with a proof tool, you could do something useful in a week, and it might be used in industry. But until then,
That's interesting.
unlikely.
Do you think we'll ever get there?
With AI, yes, it's maybe some combination of AI proofs. Although I think you're still going to need quite a lot of expertise with the difficult bits. So, but you might be able to start. Perhaps somebody can start doing the easy bits, and then you have somebody who's been doing proofs for a few months or years comes in. So you might be able to combine people who don't have much training, getting some easier bits done, help of AI, and then you say bring in the experts who have got more expertise. He's coming to help with it. Yeah, but we don't have it. So that's a suggestion for somebody to produce a tool like that.
Okay, so we've got a few questions online, but perhaps we could start the room, please. Anyone got any questions?
I'm trying to put my hand up.
What do you think about description logic?
Sorry.
Sorry.
There is a mathematical discipline called the description logic, and the description logics, it's a kind of lightweight logic for execution of proofs.
Right. Okay. Well, I don't know it. You can come and tell me over a glass of wine. If you think it's the way forward, do you think can AI help with it? Or are there any tools?
Ontologies.
Is it mathematics, or is that other?
It's the basis of ontologies.
Okay. Yeah.
So ontologies is like a modeling structure for representing like everything in the universe, or maybe some specific things in software engineering.
Well, I think that first of all, you've got to do some marketing. How many other people know about this?
Yeah.
I'm afraid you have to sell things, even if it's logic, to make. Then come up. You need tools. So can you produce tools with it?
Yeah, there are actually.
Can you scale it? It's got to be scalable.
Yeah.
So I don't. You can tell me it's an edge. All the mathematics. If you just wrote in the maths, it would be terrible. But you have the schemas to make, and then you can have thousands. So 25,000 pages of this. Enough. If you can't, then you probably need to think about how you might combine it. On the other hand, if you saw my examples for the requirements, maybe you just use the requirements level and it's still fairly small, and then somehow link it down to the line in some way. My recommendation. Yeah.
Okay, any more questions in the room?
That's a possibility.
Yes, yes.
On the subject of unification,
Yes.
has there been a rich history of attempts to translate from one specification language to another, and has that been fruitful or frustrating? Or
Well, that's what that did with different semantics. I don't know, you haven't looked at that book, you know that. Okay, well, it's got denotational semantics, operational semantics, axiomatic semantics. So it tries to basically show they're all the same, and you know how they're linked. I mean, I'm not sure how useful it is, you know, to take, say, Z and say this is the same as B or something like that. This was looking at the more mathematical aspects of programs to show, yes, different people have different approaches to specify the way programs work. So operational, very nice for engineers because it literally is operate. You do this, you do this, you do. Mathematicians prefer something slightly higher up with denotational style, which lots of funny symbols. So it sort of satisfies different types of people. And this book was to try and show, well, this is ultimately all the same. Which is a worthwhile thing to do. So,
in terms of popularizing, or at least trying to embed this in other, like a wider context, has there been any work academically to look at operational models that would include this type of like formal methods within them, like within the process of developing software, where they've said, okay, well, this is a generalized pattern that we could throw around different organizations?
well, people have looked at software patterns and so on. Yes, libraries patterns.
No, I don't mean in that way. I mean,
When you say operational, you know,
I mean, at like you're talking to a COO.
yes, yeah.
You're saying, hey, COO, I'd like you to invest some cash
Yes,
into
yes.
getting people's behavior to look like this.
Right. Well, I just say we're using AI.
Well, that would sell. Yeah, you'd get some cash for that for sure.
A little example of selling formal methods because you can't show lots of maths or something.
Of course.
So Connie Heitmeyer had to sell formal methods to naval admirals because she's in the Naval Research Lab in Washington. So yeah, no mathematics, but what we do is a nice submarine simulator with lots of things to play with. Then you just tell them, well, there's formal methods behind this too, and then they give you lots of money. So yes, you need different marketing techniques depending on. Yes, I wouldn't mention anything with mathematics to but probably you can mention AI as well.
Good way to get cash out of the machine for sure.
And as I said, I think
25.
it's a very good time to be comparing mathematics for it's we're not there yet, but the developments are just so rapid. Oral papers coming out monthly.
Okay, right, shall I go to some of the online ones? I'll do them in reverse order. Sorry, Margaret, we can't hear you in the room for some reason, but you've typed your question in. So
Yes.
Jonathan, do you think that formal methods can be boiled down to the important place logic has in the computer science curriculum? We at
Huddersfield. Huddersfield, can you hear me?
We at earlier.
Can you hear
We
me?
at Uni use MSFOL translated to Prolog to check the problem of two aircraft colliding, i.e. a by a specker limit on vertical and horizontal.
That sounds more like a comment.
Yeah, the question.
The
Yeah,
question.
it does,
I
doesn't
didn't
it?
get the question.
Can
Yeah,
you
I
say
suppose-
that again?
Thanks, Greg.
I suppose the
Yeah.
real question is, do you think that formal methods can be boiled down to the important place logic has in the computer
Well-
science curriculum?
I mean, I
Yeah.
think the curriculum,
Yeah.
formal methods has to have logic and
Yeah.
maybe set theory and things underneath it, or of some sort. I think one of the problems in the past is that we had the sort of formal methods being done silos, and then there'd be real programming, real software engineering, and not really connected between the two. Now, of course, the formal methods bit's been just removed. So. But what you should do is put some of the formal methods into the software engineering course, and which does happen. I'm exaggerating. So it should be integrated, saying these things you can do. I mean, there's some nice little tools you can in this conference I was at this week. Things like Alloy, very nice, simple tool. That is a tool you can learn incredibly quickly and do some interesting things with. So you can integrate stuff that and you don't have to call it formal methods. You know, you just say, here's a tool, we'll help you.
Okay, so we have another one here from Richier. Do you have any thoughts on property-based testing, CF Haskell quick check versus formal proofs? PBT capture most of the low-hanging fruit.
Well, I think you should use whatever approach is appropriate. You know. I mean, choosing you saw that picture that I showed with the opposing methods. There's two opposing methods. It's trying to decide. It's going to depend a lot on what you're trying to apply it to. And if, what's the system? Then you need somebody with expertise in both approaches, make some sort of estimate as to which one's going to be most useful in practice. I'm not going to do it on the fly. But whenever you have these different approaches, well, maybe they're both not too bad. Maybe one is obviously better than the other. You better try and make the right decision if there's a great difference between the two.
So I'll just pick some others here. Here's a Peter Landin question, probably lost in the mists of time. When Landin wrote the next 700 programming languages, how did he settle on 700 instead of 70 or 70?
Well, allegedly, the story goes that he wrote the next 100 programming languages. And in those days, when you had a typewriter for a one, it was a very good thing like that. And when they actually came to proof set it in a proper thing, somebody read that one as a seventh. That's the story I believe. You can't prove it now. But yes, so there's a very good reason why it might be. In those days, you wrote on a typewriter, and then you got somebody else who put it into a nice format for a journal or whatever. You might make mistakes, and I guess Peter Landin didn't proofread very well. I assume he was given it to proofread, or maybe he liked the fact that it went up from 100 to 700. So, well, let's leave it.
Okay, we have some more comments that RISC-V is the first ISA to mandate an accompanying formal spec and anointing it as the first eventual truth about the ISA. Z-Eves is one of its later incarnations was very useful for writing Z to be included in Word documents. So these are more comments really.
Yeah, well, that's great.
Tools here.
Yeah. But Z-Eves was still pretty. You had to have a lot of training to use it.
So we tried mentioning that one of his colleagues at Swansea are doing work on verification for blockchain.
Right. Well, that's another good area.
So maybe
might make a lot of money. No, I don't actually know how much formal methods have been used for blockchain in reality. Bitcoin, has it been formally verified? Or I haven't looked at it because it's an obvious area where you don't want to make too many mistakes.
Or too much things. Okay, I think time is getting tight now. I think we have.
We don't want to eat into. There's wine and nibbles.
Exactly. So my apologies if I've not been able to get around to your comment or question. But it says, sorry, Margaret. Apparently I can hear you online, but unfortunately we can't hear you in the room. So apologies for that. Okay, so I'll leave the final comment to Margaret. If you look us up, maybe you will find copies of our publication on the automated refinement of requirements domain theory, authored by McCluskey and West, published in Automated Software Engineering.
Can you save the comments?
I certainly will.
So we can have a look through.
Okay, I think
if you save the comments, you can email them to me.
I will do that. Soon. Okay, so
Brian conveyed his apologies. His last train leaves.
Yes, he mentioned that. It's fine. Yes, I said he could take some sandwiches. Yeah.
So, apart from that, unless anyone else has any more comments, questions in the room,
One last one. Maybe my naivety, but there's a tool called Infer from Meta. They when any developer does a pull request for certain systems, it has to go through what they've centralized a lot of their work on static analysis and some model checking and reachability, and that those are automated checks that are done agnostic of the language. So they'll have different transpilers or compilers to infer, and they'll have sat solvers in there and
Yeah.
all kinds of interesting stuff.
A lot of these big companies are doing formal methods things
Yeah.
with all formal methods because it doesn't. Well, certainly Microsoft is like that. And obviously, some of it you don't never get to hear about because it's all very secretive. Google don't tell you much, and so trying to get information out of. I mean, the problem in industry is if something works incredibly well, you want to keep it secret. You don't want anyone else to be able to do that. If it goes very badly, it's far too embarrassing to tell anyone. So you don't hear about it, whether it's good or bad. There's good reasons not to say anything if you're in industry.
Portions of it are open source, so you can look at the GitHub.
I know, yes, obviously things leak out. Yeah.